Hello. When working with integration, you can see that U-substitution and trigonometry go hand in hand. Sometimes the U-substitution and trigonometry help each other out. Other times they're conflicted. I guess what I'm putting up this video for is to show you that sometimes you might think that U-substitution is the most direct and beneficial path, but sometimes just using your trig identities will be enough to give you something that's integrable. Take, for example, the integral of the sine cubed of x. If I rewrite that as the sine squared times the sine of x, then my trig identity, which we should all know by now, are the sine squared plus the cosine squared of x equals 1. If we rewrite that, when we get the sine squared of x is equal to 1 minus the cosine squared of x. So now what I have is a situation where I've crafted a nice little u-sub scenario. I'm going to let u equal the cosine of x. I said this is, I guess this is an example where U-sub and trigonometry work hand in hand with the identities. So sometimes basically you have to remodify your function in order to use some trig identities to help you out. Or sorry, in order to use U-substitution to help you out. So anyway, as you can see, once I make that substitution, I can get dx in terms of du, and I can see how easy this is to integrate. And then I put my cosines back where I found them, and you can see a nice little integral. Of course, we want to check that, but that's not what this video is about. This video is about the use of identities. So here's a common identity, and in this case, you might think, hey, that's the sine squared. I'm just going to make that 1 minus the cosine squared of x dx. But then you get stuck because there's nothing to u-substitute and get rid of your dx. So you end up with a problem. The problem is we have a sine squared, and integrating the sine squared is problematic. So what we have is a power-reducing formula. It comes from our double angle identity, which says the cosine of 2x is equal to the cosine squared of x minus the sine squared of x, which is great because that means when we have the sine squared of x, we could write it in terms of the cosine of something 2x without any powers. Of course, the cosine of x, whoa, I got way ahead of myself. The cosine of x can be written as 1 minus the sine of x. So if we have 1 minus the sine of x minus the sine of x, we get 1 minus 2 sine squared of x, and that's another form of the cosine of 2x. And then the third form is we could write cosine squared of x minus 1 minus cosine squared of x, which gives us 2 cosine squareds and an extra subtract 1. So 3 different ways of writing the cosine of 2x, so that we can express sine squared in terms of cosine of 2x, and we could also express cosine squared in terms of 2x. For our purposes, we are going to utilize the cosine of 2x is equal to 1 minus the 2 sine squared of x, and we're going to solve for the sine squared. Sine squared will equal 1/2 minus 1/2 cosine of 2x, or take out the 1/2 if you want to. It's completely up to you. This is something that you'll definitely need to have access to. You can remember the identities which are in your formula packet and modify them, or you can just memorize this. It's your choice. So instead of writing the integral of the sine squared of x dx, I am going to write the integral of 1/2 1 minus cosine 2x dx. I'm going to take out the 1/2. I'm going to integrate 1. I'm going to integrate cosine of 2x. And then I got it. It's all straightened out. Just basically redistribute the 1/2, and I have my integral. Tangent squared of 2x. Now it's got a double angle and a squared. What to do? What to do? Well, in this case, once again, we are going to use our trigonometric Pythagorean identities, but they're modified. If you take the regular Pythagorean identity and divide everything by sine squared, you get a new relationship pairing up cotangent and cosecant squareds, respectively. If you take that same identity and divide by cosine squared, you are going to get the tangent squared of x plus 1 is equal to the secant squared of x. So now we have tangent squareds and secant squareds indelibly tied together, and cotangent squareds and cosecant squareds indelibly tied together, which is kind of nice because they also have companionship when it comes to derivative. Nonetheless, by changing this to a secant squared instead of a tangent squared, the antiderivative of secant squared is just the tangent. The antiderivative of secant squared of 2x is going to be 1/2 the tangent, because don't forget we have to reverse the chain rule. The integral of -1 is negative x, and we have all our points. All of these have been checked to protect the innocent. Tangent cubed. Oh no, I got the tangent squared. Now what do I do with the tangent cubed? Well, we could start with writing it as the tangent squared of x times the tangent of dx, which we could then write as the secant squared of x minus 1 times the tangent of x dx. And here, we can actually break this up into 2 separate integrals. The tangent of x is actually in your formula packet, but I'll show you how to get that without a formula packet. And over here we see a U-substitution situation because the secant squared and the tangent of x are bound by derivative. So in the first case, I'll let u be the tangent of x, d is the secant squared of x dx, and in the second case, I will let v be the cosine of x and dv be negative sine of x dx. Just a reminder that the tangent is equal to the sine over the cosine, which is cosine of x to the negative 1 times the sine of x. And so here's the negative sine of x dx, which becomes the du, and the v. So the rest of this, I am going very fast. Please feel free to pause the video and look at how everything works. The whole purpose of me talking you through this is to share with you some of my insights, which in this case, well, every time you see a trig thing, there's going to be some different catch to it, and so you have to be really well versed in your identities. That's the lesson that I wanted for you to take away here. Once you use your identities, you still might have a challenge ahead, because here we had two different substitutions that I had to apply in order to get everything integrated. And once I do, I have to put all my substitutions back into the right places and make sure everything's cool. I wrote mine as the plus the natural log of the cosine of x, but when you see the integral of the tangent of x in formula packets, they will not say minus the natural log of the cosine of x. They will say the positive natural log of the secant of x. Right over here, if you pause the screen, I'll give you a little explanation of the connection between the natural log of the cosine and the negative natural log of the secant. One last problem. This time we have the integral of the cosine of 2x over the cosine of x minus the sine of x. And here again, we've got the whole thing about trig identities. The cosine of 2x, recall, has 3 different variants, and I'm going to choose this one, cosine squared of x minus the sine squared of x. And now here, I got a little ahead of myself, and I saw the opportunity to use conjugates, so I conjugated the denominator so that I can get the denominator to look like the difference of 2 squares. Now these differences of 2 squares can divide out, and I just have to integrate the cosine of x plus the sine of x, which is easy peasy, and I've proven that it's correct using my technology. But I was kind of silly though, because if I saw the numerator as a difference of 2 squares, I could have just used factoring the difference 2 squares as the sum and difference of the square roots, and then we could divide out the cosine x minus sine x and get the really nice integral. So, as you can see, with identities, there's always more than one way, oftentimes more than one way, to get where you're going. Sometimes it's a quick path, and sometimes it's a long roundabout way. The only way you're going to get better at any of this stuff is with experience. So take the time to absorb what's in here. I'll have the notes posted, and you can just study them as you need. Thanks for watching.